Now we move on to talk about data types, approximation, and errors. I'll leave it up to you all to review this and be sure that you understand the course content and that you can perform the different tasks I explained here. This is always very important to go through after reviewing the course content. Good. Now we move on to talk about approximation. So we use approximations a lot in petroleum engineering. You probably already learned about how to do approximations in calculus when you find the derivative to complex functions using the numerical derivatives. There is also numerical integral. So we have the option of using trapezoidal rule, Simpson's rule to find the area under a curve. Those are all approximations, and we will talk about those shortly. The goal with approximation is to be able to compute a quantity that is close enough to the true value of the desired quantity. So typically, computing this true value is very difficult, and in some cases the true value does not exist. There is no way to find out the true value. So we have to be able to come up with an estimate that is close enough to the true value, and we need to be able to find out if your value is close to the true value, which might sound a little confusing in the sense that if you don't know the true value, then how do you know if you're close to it? Well, we have some numerical techniques to figure that out. It typically is based on the change in that value from one iteration level to the next. If the change is big, going from one iteration level to the next, then it means you're probably still far off from the true value. But when that change becomes very small, like on the order of several decimal places, then you are getting closer and closer to what the true value is. That is the assumption. Good. So like I said, many times it's very difficult to compute the true value, and sometimes it's totally unknown. Examples of approximations includes fitting a straight line equation, which is y equals x plus b. This is the slope, b is the intercept. When you fit a straight line to a data set, and I'll show examples of this, when you fit this equation of a straight line to these data sets, what you're doing is you're coming up with an approximation to the data points. It's not all about straight lines, right? Sometimes we fit curves, polynomial equations, exponential equations, power law models to data which could be non-linear. That is all approximations. And I give you some examples of non-linear approximations. Like I mentioned earlier, finding the area under a curve using either trapezoidal rule, Simpson's rule, or numerical quadratures. These are all different ways we can find the area under a curve. And finding the area under the curve is equivalent to what operation in calculus? Integration. So if you have a function like this, so this is your function f of x, the integral of this function within a range is basically the area under the curve within that range. So that area under the curve is the integral of f of x with respect to x. So f of x dx, where this is x. And like I said, you can find the approximate integral using numerical quadratures using Simpson's rule or trapezoidal rule. And we'll talk about that some more. So here I'm showing you actual data. This is flow rate in stock tank barrels per day. So it's barrels at surface conditions, barrels of oil at surface conditions per day. So that's the rate, and this is time in days. And you see the production rate drops through time, and this is what you typically will observe in oil production wells. And what we have done here is to fit a curve through the data set. You can see in general that curve passes through most of the data set. That curve is an approximation to the true value of the production rate. And in this case, what we fitted through the data is a logarithmic trend line. And you can see it's a logarithmic trend line because the equation of the line uses the natural logarithm of x. So it looks like the equation of a straight line, except that instead of x, you have the natural logarithm of x. And that is precisely what you get from exponential models, which I'll talk about later. This quantifies the degree of the goodness of fit. The closer it is to 1, the better is the fit. So this is just okay. We'd like this to be close enough to 1. If it's like over 90%, then it's a lot more accurate. But sometimes the data is just so noisy, so there's no way you're going to approach to 1 when you have some data points this far off from the general trend. So outliers will destroy this value in general, and that's what you see here. So these points are far from the curve, and they are also far from the other points. So it's just the nature of the data. That's why the R squared appears to be weak. So these dots, again, they are from the Volve well, this particular Volve well, and I shared all of the production data from the Volve field on the GitHub page for this course, and we'll be plotting it using Python. We'll be doing all sorts of calculations on those to give you experience actually running code to do useful stuff on actual production data. So one common technique in petroleum engineering is to transform data sets such that they line up in a straight line. So these green dots, which represent the historical production rates, they are non-linear, just from the trend. That's ignoring this red line we have in there. The true data itself, the green dots, are non-linear. What we typically do in petroleum engineering is to find a transformation to the x-axis or the y-axis, or both of them. So maybe instead of plotting time in days, we plot the natural logarithm of time. So we're plotting oil rate against natural logarithm of time, and you want to find out, does that make the dots now line up as a straight line? If that doesn't work, how about if we plot the log of the oil rate against the log of time? Does it give you a straight line? What if we plot the oil rate against cumulative oil production? Does it give a straight line? And we keep exploring different transformation of the data set. Why? Because when your data set lines up in a straight line, then it's very easy to fit a line through it and then extrapolate the performance into the future. That's what we are more interested in. We don't just fit curves or straight lines through a linear data set. We also tend to extrapolate it out into the future, and then we can make predictions of, say, the oil rate after 10 years. Right now, you're looking at production over 200 days. So if we fitted a straight line through the data set and this was 200 days, well, you can extrapolate that trend line out into the future, and you can make a prediction of what the oil rate will be in 15 years' time. That's the real reason why we do these predictions.